In this video, we're going to determine the relationship between the mass of an aluminum disc and its diameter using the technique of graphical analysis. The measurement devices that I'll be using today are different from those that you've used in lab. I'm using a less expensive balance. Its accuracy is only plus or minus 0.1 grams. In lab, you'll be using a more accurate balance. The caliper that I'm using is a caliper that is better and more accurate than the one you're using in class. It will give us diameter measurements of plus or minus 0.001 centimeters. The aluminum discs that we'll be measuring are also shown in the same photograph, but bringing your attention to disc number 5, we're going to consider this one to be our unknown. And while we will measure its mass, we will not measure its diameter. Rather, using the result of our graphical analysis, we will make a prediction about its diameter. Using my top loading balance and my electronic caliper, I have determined the following measurements. The masses and the diameters are shown on screen. Recall again that my mass measurements are plus or minus 0.1 grams, and my diameter measurements are plus or minus 0.001 centimeters. And in fact, these uncertainties in my measurements exist for all of my measurements. Having this data to work with now, what I need to do is take this data and enter it into an Excel spreadsheet. The data will need to be copied over. Let's do that. I'll go ahead and paste in the handwritten data here that we have to work with, and then we'll begin entering the data into the spreadsheet. We'll want to be organized about this. I'll have vial number. I'm going to put that in a different place right here. And I'll put mass on the left for a reason that I'll get to in just a moment, and it has units of grams. And I'll put diameter on the right of mass, and it will have units of centimeters. Now, the reason that I'm ordering my columns this way is quite important, as mass is going to be the independent variable, and Excel always likes to see the independent variable, which is x, to the left of the dependent variable, which is y. The order of these columns is important. We want whatever is going to appear on the x-axis of my graph to be on the left, and whatever is going to be on the y-axis of my graph to be on the right. Our vial numbers, we can enter those easily, 1, 2, 3, 4, 6, and 7, where vial number 5 is going to be our unknown. The masses we can also enter very quickly, just from the data table. We have to go through all of them, though, and enter them carefully, avoiding any mistakes. And 21.3. So there are 1.6, 3.3, 4.3, 6.1, 12, 21, and of course vial number 5. I'll enter that here, although it will not be part of the graph. This is a number that we'll use in the graphical, once we get to the end of the graphical analysis. Diameter, okay, 1.853 and 2.627. 627, there we go, and 2.972, and 3.590, 5.006, and 6.666. Very good. Now, we've got all of that information entered, and we're good to go. We could even proceed with creating the graph. But before we create any graphs, let's go ahead and create some additional columns. The graphical analysis exercise that you'll be asked to perform with the steel spheres will require you to calculate diameter squared, diameter cubed, diameter to the fourth, square root of diameter, and so forth. So I'm going to create some additional columns here that utilize the diameter information that I have. Let's begin with diameter squared. Now, diameter squared, in order to make it look like diameter squared, I'm going to go up here, highlight the two, right-click, Format Cells, make it a superscript. There we go. Now I've got diameter squared, but that also applies to the units. And the units are squared as well. So let's do it this way. I'm going to go back over here, highlight, Format Cells, and make it a superscript. So not only the column header diameter is squared, but along with it, the quantity centimeters is squared too, because that's what the diameter is measured in. To calculate the diameter squared is really quite easy. All you need to do is type in an Excel formula. They begin with equals. What I'll do is I'll take the contents of cell L4 and I will use the caret symbol and the number of 2 to square it. This formula will take whatever's in L4 and it will square it. And enter, and there is our result. I don't need to re-enter that equation, however. I can simply click on the original cell that has the correct equation in it, position my cursor down here in the lower right-hand corner where you see that little handle, click and drag, and now I have all of the squared values. While I'm at it, I'm also going to go ahead and, for this exercise anyway, do diameter cubed and centimeter cubed, where we need to insist that that 3 be superscript. And that applies also here, and I guess I've got things in parentheses, so let's just be consistent throughout and highlight that 3 and make it a superscript. Very good. Again, a formula is used to calculate the cube of the diameter equals, I'll grab L4 a little differently this time. Rather than enter L4, I'm just going to move my cursor over and click on L4. Note that it enters L4 automatically. A caret symbol, and then 3 to cube it. Hit an enter, there it is, the cube of the diameter. Click and drag on the handle in the lower right-hand corner, and I have values for all of the diameter cubes. Okay. You'll be creating some additional columns. I'm only going to take this through diameter cubed, and now we need to graph. The graphing part of this goes actually quite nicely with some shortcuts that I'm about to show you. First note, again, that the X column and the Y column for the first graph that I create, X's, or the independent variable, always to the left. It's what Excel expects to see. X values to the left, Y values to the right. When selecting data for a graph, however, only choose or drag over the numbers. Don't pick up any words or additional extraneous information. Only the actual measurements should be part of this process. I've selected the X's and the Y's. I next go to Insert, Charts, and I'll pick this very first scatter plot. As you can see, the graph looks consistent. There seems to be a pattern here. None of the data points really fall out of line. They are all following a path. However, that path, as I hope you can see, is not a straight line path, and that's something to keep in mind as we create the trend line here in just a moment. Okay, so let's clean this graph up and make it more professional. The title of this graph will be diameter. Okay, let's spell it right. Versus, let's get the units in there as well, versus mass in grams, like that. Okay. The title, though, should include some additional information. So I'm going to go back and edit it, hit an enter. I'm going to enter my name, the experimenter, and the date that I'm doing this experiment, like so. I like to see titles boldface, and I like to see the lower line actually. Let's get that here. Highlight it again. Smaller font. I'm going to bring that down to 8-point font. Makes for a more professional looking graph, some attention to detail, always nice to see. Next, we need to add the axes titles. I'll activate the axes titles. They're now available for me to edit. I'll begin with the x-axis title, which will be simply mass. And it needs to reflect the units that are being used. The y-axis title is going to be diameter, and the units for this one are going to be centimeters. There we go. My graph is looking good. Inspecting very carefully for any sort of typos. Don't see any title, axes titles, y-axis, x-axis, looking fine. Next step, create a trend line. Position your cursor over any of the data points. Right-click. Add trend line. On the right, in the window that opens, you'll see that linear trend line is the default, and that is exactly what we want to be using here today. Furthermore, at the bottom, we'll want to display the equation and display the r-squared value on the chart. Done with that window, I'll close it. Let's return to the graph. Two things of note. In the graph, as you can see, there is a dotted line which is straight. This is the linear trend line. Note that the linear trend line attempts to go through the very middle of the points, keeping as many to the top as to the bottom. But we already noticed that there was some curvature and that a straight line wasn't going to be a very good fit. The trend line equation is of the form y equals mx plus b, which is to say slope-intercept form. Turn your attention to the r-squared value. In this case, r-squared is 0.9751. The closer r-squared is to a perfect 1.0, the better the data fits this straight line. Now 0.9751, not bad, it's close to 1, but as you can see, some data points are not on that straight line because our data has curvature. We expect to see better agreement than what we're seeing right here. And thus, we need to continue with our graphical analysis. Let's back away from this for a moment and see what we've got. Okay, diameter versus mass was a good start. In fact, this graph has all of the formatting that I need for all of the other graphs that I'm going to create. Let me show you a simple, straightforward way to create additional graphs. Begin by clicking on the graph that you've already spent some time formatting. Then right-click and copy it. Next, click outside that graph to a different place in the spreadsheet and paste the new graph. I've just created a graph that is the identical duplicate of the first one that I created. However, in a moment, I'm going to make this graph, instead of diameter, I'm going to make it diameter squared. So I'm going to go in here and use the font key to create superscripts. This is all necessary to make the graph at least look good. And it's not over yet because I've got diameters that need to be squared here. Right-click, font. I'll do this as quickly as I can. Superscript. And I also need a 2 in the unit. So there we go. Font and superscript, and OK. Now, the graph that I'm showing you here, the one to the right, I have every intention of making it diameter squared versus centimeters versus mass. But it doesn't currently display that information. It's still referring to the diameter column. So clicking outside this graph and then clicking in it again, bring your attention back up here to the data table. OK? The data table currently is highlighted, the two columns with mass and diameter. These highlighted columns are what the graph is currently using or displaying. And what I would like to do is not display diameter, I would like to display diameter squared. And this is an easy change to make. I'll position my cursor on the boundary of the blue box. I'll click and I'll drag that over to highlight diameter squared instead. I am now moving the dependent variable focus of my graph to the diameter squared column. And when I release, the graph instantaneously updates. And better yet, not only does it update, but so does the trendline equation. You'll notice now the trendline equation of this new graph is not the same as the trendline equation of the old graph. In fact, looking at the r-squared value, I'm encouraged to see an r-squared value that's very close to 1. This is a very good result. But while we're at it, let's go ahead and create a new graph. I'm going to copy this second one, and I'm going to paste it again right there. Things are getting a little bit squeezy. Let's back away from this and rearrange my graph so that we can see everything on screen. I've already got a great result with that diameter squared, but let's also, just for review, look at diameter cubed. Okay, well, I've got to get it cubed. You know, having done the superscripts now, for the second graph, I can go back, and using the second graph as a template, I can go back and simply replace the 2's with 3's and create a diameter cubed graph. But as was the case before, remember, this is a graph that's currently displaying diameter squared information, whereas I want it to display diameter cubed. So you click on the graph to select it, you go to the data table, and you grab the blue boundary, the dependent variable, and you move it over to diameter cubed. And there you go. And you can see that the diameter cubed graph isn't really fitting the data. The trend line isn't fitting the data as well as the diameter squared. So as we look at the 3 graphs that we've created, we focus our attention on the trend line, and you can visually see which trend line fits the data points best. But you can confirm that by looking at the r-squared values, because our second graph of diameter squared versus mass clearly has the best r-squared value of all of them, being a perfect 1. But is it? We don't know for sure because there's just a little bit more work we now need to do. Our biggest job is behind us, as we have identified the diameter squared graph as the one that we should be using in any sort of graphical analysis prediction. But to avoid rounding errors, there's one last thing that we need to do. I'm going to click on the trend line box. I'll right-hand click on its boundary. I'll format the trend line label, and then from the category, I'm going to pick number and increase the number of decimal digits to something ridiculous like 8. What this does is it creates what has been in the past hidden from us. It displays more fully the actual trend line equation that we have to work with. Furthermore, as you can see, the r-squared value, although it is very close to 1, is not perfectly 1. The one that we saw previously was rounded. This r-squared value is being displayed more fully to demonstrate how it isn't perfectly 1, but it's really close. All right, so the worst part of the graphical analysis is over at this point, and we have the desired result. Our diameter squared graph is the one that we should be using to determine the diameter of the unknown disk number 5. And we can do that now very quickly, now that we know the correct trend line equation. So let's do that. I'm going to move, whoops, we'll leave that graph right where it's at. I'm going to remember that the mass of the unknown ball bearing was 7.5 grams, and we'll go off here to the side and just keep track of that information that we've got. Okay, so we've got a trend line equation that is the best trend line equation, as it has the best r-squared value, 2.08470 175 x plus, I'm getting it in all of its glory, 03911 820. Okay, so what is this really telling us? Well, it's telling us about y. And it comes from a graph where it was diameter squared. So y is actually diameter squared. And that is equal to 2.084700175. X is mass. So this should be multiplied. I'm just going to put the word mass in here. And then we have plus 0.0391182. Squeeze it in there. This step is actually quite important because although it's tempting to see, X is mass, I'll just plug it in and I'll get an answer. The answer that you're getting when you use this trendline equation is not the diameter. It is the diameter squared. And so what we'll do is we'll go ahead and continue with this algebra, which is to say that 2.084700175 times the mass, which is 7.5 grams, for our disk number 7, plus 0.0391182. Okay, I'll grab my calculator here. I could do this on Excel easily, but I'm going to go ahead and just type these numbers in. 2.084700175, I think I got it, times 7.5 is equal to, and then I need to add plus 0.0391182, and I get a result that the diameter squared is equal to 15.6743. Got that right, 67438. All right. That is actually the diameter squared value. If we want the diameter, we will need to take the square root of both of these sides of this equation, and that will return the diameter. And if I do that using my calculator, I find that the diameter is 3.959 centimeters. And that is for disk number 5. And in fact, that is exactly what the diameter of disk number 5 is. To recap, what we've done here today is we have taken our diameter and mass information, put them into a spreadsheet, and created 3 graphs. You will create more graphs than that. And of those 3 graphs, we find the one that best fits a straight line. We increase the accuracy of our trendline equation, and we use that trendline equation to calculate, in this case, diameter squared. And then, remembering that it's diameter squared and that our answer needs to be diameter, we take the square root of both sides, and we determine that the disk diameter for number 5 is 3.959 centimeters.